In this video, we'll briefly discuss the concept of voltage and current and review the requirements for a complete electrical circuit. We'll finish up this review with Kirchoff's rules and describe one or two examples utilizing these rules in electrical circuits. When we talk of voltage, we typically associate it with a device that provides current or power. These are referred to as batteries. This is just one of generally two types of current sources, which is called a direct current source or a DC source. The other type is the alternating current source or an AC source. The voltage provided by such DC sources or batteries is constant and does not change through time, until of course the batteries run out. Batteries are characterized based on the voltage they supply, their power density, and/or the amount of current they supply over time. The voltage density describes the amount of power per mass volume that a battery can supply over a period of time. For example, a power density of 100 watt-hour per kilogram describes a battery that can supply 100 watt per kilogram of power over 1 hour. So a AAA alkaline battery is 11.5 grams, then the power supplied by this battery is 100 watt-hour per kilogram times 0.0115 kilograms or 1.15 watt-hour, or 1.15 watts in 1 hour. The most commonly used batteries are alkaline batteries, typically constructed with zinc core and a manganese oxide covering and a potassium hydroxide, which is an alkaline substance, as the electrolyte. These are non-rechargeable batteries, but can practically be used in any portable gadgets such as flashlights, wall clocks, wireless microphones, keyboards, and a mouse, to name a few. They typically supply 1.5 volts to 9 volts of voltage and have a power density of 100 watts per hour per kilogram. Another type of non-rechargeable battery is a lithium cell. Lithium and silver oxide are the electrolytic substances that are used. It can provide a voltage of 3 volts and much higher power density of 270 watt-hour per kilogram compared to alkaline batteries. Because of this, lithium cell batteries can be made much smaller than alkaline batteries. This makes lithium batteries ideal for smaller devices, such as a watch or a laser pointer. The commonly used types of rechargeable batteries are the nickel-cadmium or the nickel metal hydride, lithium-ion polymer, and lead-acid batteries. Nickel-cadmium and nickel metal hydride batteries supply 1.2 volts and are often connected in a set of 3. It also has a power density of 60 watt-hour per kilogram to 100 watt-hour per kilogram. Nickel metal hydrides are more desirable as an environmentally friendly alternative to alkaline lithium and nickel cadmium batteries. Lithium-ion and lithium-ion polymer batteries has a voltage of 3.7 volts with a power density of 126 watt-hour per kilogram to 185 watt-hour per kilogram. Lithium-ion batteries are ideal for mobile phones and similar mobile devices. Lithium-ion polymer batteries can be found in drones since they provide more power, are robust and flexible, and has a lower chance of leaking electrolytes. Lead-acid batteries provide larger voltages from 2 volts to 24 volts, but has a smaller power density of 7 watt-hour per kilogram. These are typically used in uninterruptible power supplies, or UPS, robotics, heavy machinery, and in cars. We'll talk about the response of the electrical components of DC and AC sources in the next couple of meetings. Due to the applied voltage, charges are able to move through a wire. The movement of these charges are what's responsible for the current. Current is the movement of these charges and is quantified as the amount of charge traveling through a wire per unit time. 1 ampere is equivalent to a total charge of 1 coulomb passing through a cross-sectional area in 1 second. 1 coulomb of charge corresponds to 6.25 times 10 to the 18 electrons. Let's take a look at the most commonly used symbols for voltage and current sources. Going from top to bottom, left to right, we see that the electrical symbols for DC voltage, AC voltage, variable DC voltage, DC current, generator, and the AC current. By convention, the number of short and long pairs of straight line in the DC voltage and variable DC voltage indicates the number of batteries required. The second symbol for DC voltage is not so often used. These symbols are electrical symbols for voltage sources. The symbols for the DC and AC currents are electrical symbols for current sources. The generator symbol is also not so often used in electrical circuits, but can still be quite useful for descriptive purposes. There really is no true current source. Current is driven by a voltage, but you can create a very simple current source by using a variable resistor to a voltage source. Whether you need a voltage or a current source will depend on the application. Let's now explore other basic electrical components that we will need to use in order to build electrical circuits. The first two symbols you see are the symbol for a variable resistor and potentiometer. As we've seen in the previous video, the potentiometer has 3 terminals. These 3 terminals are seen in the potentiometer symbol, but not in the variable resistor. If the variable resistor has 2 terminals, then it's just a rheostat. A preset potentiometer is just a potentiometer with a preset value that can still be changed. PTC and NTC thermistors are variable resistors that change resistance due to changes in temperature. It's a thermal resistor or a thermistor. PTC stands for positive temperature coefficient, while NTC is for negative temperature coefficient. PTC thermistors increase in resistance with increasing temperature, while NTC thermistor increase in resistance with decreasing temperature. The voltage-dependent resistor changes resistance when there's a change in the voltage, and the light-dependent resistor changes resistance with the intensity of light. Similar to symbols for resistors, the symbol for a variable capacitor is just the same with a fixed capacitor but with an arrow, and with a preset capacitor but with a flat-headed line. An electrolytic capacitor is symbolized by either black and white plates or by plates with positive and negative charges. A fixed inductor without any core is symbolized by semicircles with lines at both ends. Add an arrow to that symbol, we have the symbol for a variable inductor. And a flat-headed line, we have a preset inductor. With double lines to the right of the inductor symbol, it's either an inductor with a ferrite core for dashed double lines, or with an iron core for straight double lines. Finally, the large symbol with the line at the top of the black triangle is the symbol for a diode. A picture of an actual diode is shown under the symbol. We'll learn about diodes later when we discuss semiconductors. We will also be needing switches to turn on and off the current supplied to these components. There are single pole, single throw or SPST switches, single pole, double throw or SPDT switches, double pole, double throw switches. We also have push button switches and a rotary switch. The 1P4W stands for single pole 4-way switches, but it's generally a rotary switch. Finally, let's review Kirchoff's rules. There are 2 of them, and they are simply named the loop rule and the junction rule. The loop rule is used to determine relationships of voltages around the loop, while the current rule is used to determine relationships of currents through a junction. The loop rule states that the algebraic sum of changes in potential around any closed circuit path or loop must be zero. In the circuit, there are three loops. We have loop 1 passing through points A, B, C, D, E, F, G, H, L, and J. We also have loop 2 passing through points A, B, C, D, E, L, and K. Finally, we have loop 3 passing through points A, K, L, E, F, G, H, L, and J. Note that we have chosen a loop direction in the clockwise direction. It is also correct to choose a counterclockwise loop direction. The junction rule states that the sum of all currents entering a junction must equal the sum of all currents leaving the junction. In the example circuit, we have two junctions at points A and E. We chose an arbitrary direction for the currents at point A. I1 and I2 are the current directions leaving junction A, while I3 is the current direction entering junction A. Similarly, I1 and I2 are the current directions entering junction E, while I3 is the current direction leaving junction E. Following the chosen loop direction, we consider a voltage drop between the two voltage points or voltage terminals, that is a negative voltage, if the loop direction is from the positive terminal to the negative terminal. Otherwise, consider a voltage increase between the voltage points or voltage terminals. Also, following the loop direction, we consider a voltage drop across the resistor if the loop direction and the current directions are the same, and a voltage increase otherwise. These simple guides to whether there is a voltage drop or increase across the components is shown in the left figure. To solve the problem, we need to compute for the currents I1, I2, and I3. If we now apply Kirchoff's rules, specifically the loop rule, we get the following equation for loop 1. I1 R1 plus E1 minus I1 small r1 minus I1 R5 minus I3 small r4 minus E4 minus I3 small r3 plus E3 minus I3 R3 equals 0. For loop 2, we have minus I1 R1 plus E1 minus I1 small r1 minus I1 R5 plus I2 R2 plus I2 small r2 minus E2 equals 0. At this point, we note that the equation derived from loop 1 relates all variables along the wire with current I1 and along the wire with current I3. We also note that the equation derived from loop 2 relates all variables along the wire with current I1 and along the wire with current I2. Thus, it will no longer be necessary to derive another equation from loop 3 since it will be redundant. Generally, we only need n-1 loops to solve the problem. Utilizing the junction rule, we obtain the following equation. At junction A, we get I3 equals I1 plus I2. At junction E, we also get I1 plus I2 equals I3. In general, we also need n-1 junctions to solve the problem. Substituting the given values to the equations and ignoring the units temporarily, we end up with the following equations. We now have three equations with three unknowns, with I1, I2, and I3 being the unknown quantities. Solving the systems of equations, we initially get the values of the currents I1 to be equal to negative 0.3498 amperes, I2 equal 0.3853 amperes, and I3 equals 0.0355 amperes. We can then easily obtain the voltage across all resistors. They are listed down as shown, rounded off to the correct number of significant figures. Don't forget to check your answers. After plugging in the currents to these equations, we observe that all derived equations are consistent. It should now be easy to solve for the power dissipated by each resistor. We can use any of the equations listed. The power dissipated by each resistor is listed down as well. Now that we've gone through reviewing some of the basic concepts necessary for the course, we are now ready to proceed with the new concepts. In the next video, we will learn about the concepts of phasors and how they can be used in analyzing electronic circuits. See you then!